Earth scientists like myself have been working for many years to understand Victoria's geology. Our problem is that the deeper crust below about 2 kilometres has been out of our reach. And this is the very region that we think may hold the answers to some big questions. Questions like, how was Victoria assembled? And what role did faults play in forming the goldfields? But now, because of a new seismic survey in northern Victoria, we're about to get some answers. This remarkable technique uses sound waves to create an image of the Earth as far down as 60 kilometres. This seismic survey is a collaboration between government, industry and universities. The survey line is nearly 400 kilometres long, extending from Stawell to Violet Town, then north to Cobram. The line was placed near Victoria's richest gold regions, but through an area that suited the seismic method, as Ross Cayley explains.
When we were designing this route, we had to take into account the geology, which is the primary aim of the survey, but also we had to design the route so it would avoid towns and avoid busy roads and also keep as straight as possible. So it was really quite a complicated task because Victoria's got a high population density and the geology is also quite complicated.
The seismic method is a bit like an ultrasound, except it uses low frequency sound. The sound waves are generated by vibrator trucks. These slowly move along the survey line, stopping hundreds of times to vibrate the ground. At each stop, the vibrator pad is activated for 12 seconds, vibrating over a preset range of frequencies. Considering the great depth the vibrations penetrate, it's amazing that it doesn't have more effect at the surface. What's amazing is that the trucks don't seem to generate a lot of energy. Standing here just about 80 metres from them, I can only feel a slight vibration. Yet this is enough energy to send waves down at least 35 kilometres, and they bounce back to the surface. And that's an incredible round trip of 70 kilometres, all in about 15 seconds. The reflections are detected at the surface by hundreds of geophones. These are spaced about 3 metres apart, spread out over a total line length of about 10 kilometres at a time. The ability of the geophone to convert the reflected energy to an electrical signal is the key to the system.
Okay, here we have a cutaway of a geophone. They're basically a magnet with a coil of wire around the outside. They pick up little minute vibrations. The magnet in the coil moves around the magnet, produces a very small electrical voltage which travels down the cable into the acquisition system.
And this is located in the control van.
This is mission control for our operation here. Everything that's happening out there that on our line and with our vibrators is all controlled through here.
At the heart of the system, computers control the timing and frequency of vibrations. The geophone signals are processed by the computer, then stored on tape for later analysis. After the survey, more extensive processing will turn the crude field plots into the final images. These will highlight different packages of rocks and major faults. This is what Earth scientists look forward to, using the images to trace surface features to much greater depths.
Up until now, geologists working in this state have had to use surface mapping to infer the presence and geometry of structures at depth in the crust. This new seismic data is a fantastic new data set that allows us to directly image these structures, and that either confirms the dip of structures we already knew about or suspected, but has also thrown up some completely new structures that we've never even suspected in the past, and this is a fantastic boon for future research.
But why is it so important to trace faults? One reason is that the faults form the boundaries between Victoria's building blocks, called zones. The shape of the faults will tell us how the zones moved against each other as Victoria was being assembled. Faults are also of great interest to researchers like Dr. Tim Rawling. He will use the seismic data in his study of the way gold deposits were formed.
We really need to understand what the geology or what the shape of the rocks is beneath the Earth's surface. And the reason we need to understand this is because when in places like Victoria where we have a lot of gold, the fluid that contains the gold comes up along faults. So we need to understand the shape of the faults, and it ends up being like a big plumbing system. And if we can understand how the plumbing system evolved and the shape of it, then we can potentially find other areas where there is gold.
So the geometry of the whole fault network must be very important.
Yeah, absolutely. And the thing that we didn't really have very good control on until now is how deep these faults go and how they interact with each other at great depths. So now we can understand these relationships down to 40 or 50 kilometres beneath the surface.
Gold, dissolved in hot fluids, was channelled along the fault network. From deep in the crust, the fluids forced their way up faults and fractures, finally to be trapped at higher levels.
But often in these systems you don't just want to find the biggest fault, because often you can find a very big fault which had a lot of fluid go along it, but typically the gold deposits sit on little faults that interact with that fault somehow at depths.
To help his understanding of the fault systems, Tim is building a three-dimensional computer model.
So this is one of the cross sections I was talking about, and you can see that we can trace out these faults.
He starts by drawing a set of parallel cross sections that are based on existing mapping and geophysical data such as gravity and magnetic images. The cross sections are then placed in the computer. The three-dimensional model is finally created by linking individual faults and other geological boundaries from one cross section to the next. It will take about 12 months to process and interpret the raw data from the survey, but the full value of the information will continue to be realised over many years. It will remain a primary source for future ideas and models. The project has opened the door for predictive models that one day may lead us to undiscovered mineral deposits. And the survey will have a profound effect on the way we understand Victoria's evolution.